Okay, thank you. I think this is working. So the work I'm going to talk about today is done with a couple of my graduate students, Adam Ridbeck and Justin Whitaker at Colorado State University. And it's funded by the National Science Foundation in the United States. And what I'm going to talk about today is the origin of East Pacific easterly waves and an upcoming field program that's actually currently happening in Costa Rica that is studying easterly waves as well as other forms of precipitation processes in the eastern Pacific. So the first thing I want to do is give a little bit of an introduction to the phenomenon that I'm going to be talking about here. So what are easterly waves? And so I'm going to flip through a series of slides here, and you'll see the movie on the upper left animating as I flip through them. So easterly waves are tropical disturbances that we call synoptic scale disturbances. And what that means is that they cause variations in wind and precipitation on 3 to 10 day time scales. And their size tends to be about 2,000 to 4,000 kilometers across. And they move westward with time, and so the speeds at which they move westward are about 6 to 12 meters per second. The area that traditionally has been considered a genesis location for easterly waves is Africa. So if I move forward on these slides here, what you could see are two fields. The colors are precipitation, and the other field on here, which is a little bit faint on this slide, is actually rotation, or vorticity as I call it. And what you could see here is that with time, and I'll flip through this again, just so you could get a better sense. With time, these wave disturbances form over Africa and then move towards the west with time. I'll talk about their importance in a little bit. They're a big genesis mechanism for hurricanes and tropical storms, which is one of the reasons why we study them, but there's other reasons why as well. On the bottom right here, I have a plot that is called track density, and this plot essentially shows where most of the easterly waves track across both the Atlantic and the Pacific. You could see over Africa here, the waves forming and then moving westward into the Atlantic. But you also see, interestingly, and this is going to be the topic of my talk, another wave track here over the eastern Pacific, just to the south of the Central American and Mexican coast. This is what I'm going to concentrate on. This plot here also brings up a very interesting issue about easterly waves, in that there's a break in the tracks between waves that form over Africa and the waves that exist in the eastern tropical Pacific. And so one of the issues of my talk that I'm going to discuss is whether or not these easterly waves that occur over the eastern Pacific are formed locally here, or there are African easterly waves that re-intensify when they get to the eastern Pacific. So let's zoom in on the eastern Pacific now and look at what these waves look like. So this is a plot of rotation in contours, and you could think about the colors as being representative of where you have precipitation variations or convection. So everywhere you see here blue, that's enhanced precipitation, and everything that you see here reddish and yellowish, that's suppressed precipitation. So the easterly waves in the eastern Pacific have a very interesting structure. You see that they tend to originate down here and then propagate off towards the northwest with time. But what's also really interesting about them is that they tend to be tilted from southwest to northeast. And this tilt is actually indicative of some of the processes that help to maintain the strength of the easterly waves that I'm going to talk about in a little bit. Generally, also about the easterly waves in this region, you tend to have enhanced precipitation where you have what we call positive relative vorticity, and this basically means counterclockwise rotation around the circulation centers. That tends to be where you have your enhanced precipitation with these disturbances. Okay, so this is going to be the focus region for my talk. Okay, so why study easterly waves? One big reason that people study easterly waves is that they seed the majority of East Pacific tropical cyclone formation. This is also true in the Atlantic as well. So they're very useful to study for the purposes of predicting tropical cyclones. Another reason is that they're just generally important for producing precipitation. So for example, 25 to 40% of convective clouds in the East Pacific intertropical convergence zone are thought to be associated with easterly waves. They have important feedbacks onto climate. I won't talk about this, but we've looked at this in some of my previous papers and also other previous papers. They're also a very important source of precipitation in the tropical Americas that like people like Christian have looked at in some of their studies, including this paper that's in review in Journal of Climate or Climate Dynamics, yeah. But I also think their easterly waves are just interesting from a pure science standpoint. They're just fascinating disturbances that we don't really have a good grasp of the dynamics yet, and so it's a really interesting, pure intellectual exercise to study these phenomena. All right, so I'm not going to go into too much depth on this, but I just wanted to broadly talk about, what are the major energy sources for easterly waves. There's two thoughts on this. One of the major energy sources for easterly waves is thought to be interactions with the mean flow. So for example, if you have a jet stream, like you do over the Caribbean, like here, associated with the Caribbean low-level jet, that then goes into the Eastern Pacific, the easterly waves can draw energy from that jet. So that's one major energy source for easterly waves. Another major energy source for easterly waves is atmospheric convection. So when you have precipitation processes in association with convection in the tropics, those release latent heat to the atmosphere. That latent heat could drive vertical motion, which helps to spin up easterly waves. So that's another big generation mechanism for easterly waves. When you look at the relative magnitude of those two different energy sources in the Eastern Pacific, you actually can see that convection is about twice as important as energy extraction from the jet. If you just do a basic kinetic energy budget, for example, of the easterly waves. So maybe a little bit misleading because I don't really think you would have convection generating easterly wave energy if you didn't have, the jet and energy extraction from the jet first. So you have to sort of think about the feedbacks between the two. But regardless, interactions with the mean flow and convective invigoration are two really important mechanisms for getting the waves going. The importance of things like the mean flow in the jet for invigorating easterly waves has actually been demonstrated in the scientific literature. For example, there are variations associated with the midsummer drought of the Caribbean low-level jet and flow in the Eastern Pacific. So for example, this is a climatology during August. This is a climatology during September, and you can see that the Caribbean low-level jet and the low-level easterly flow in the Eastern Pacific is stronger during August than it is in September. So there are actually variations associated with the jet that produce variations in the strength of easterly wave activity that's shown on this anomaly plot here. So things like the midsummer drought cause variations in the low-level flow, but there are also other variations associated with more transient disturbances that can perturb the flow to produce variations in easterly wave activity. One of these disturbances is a phenomenon called the Madden-Julian oscillation. The Madden-Julian oscillation is often called the tropical intraseasonal oscillation because it causes 40 to 50-day variations in winds and precipitation across the tropics. And it affects places like the eastern Pacific. This is one plot done by researchers here, showing that the Madden-Julian Oscillation causes periods of enhanced and suppressed precipitation over the eastern Pacific. And these variations cause variations in the strength of easterly waves and also their tracks. I'm not going to get into too much detail on here, but just to note that there are important sub-seasonal variations in the easterly wave activity. Okay, so getting back to sort of my first summary slide where I showed this break in easterly tracks between the Atlantic and East Pacific, there are actually, and I'm dropping stuff, two views of how East Pacific easterly waves originate that are sort of competing with one another. As I mentioned later, I don't think they should necessarily be competing with one another, but there seem to be two camps at the moment. One view is that East Pacific easterly waves are essentially Atlantic easterly waves that are generated over Africa, travel across the Atlantic, weaken, and then get reinvigorated in the eastern tropical Pacific. So there's a series of papers here that sort of espouse that view. And that view is actually often invoked by places like the National Hurricane Center in the United States, where they argue that they can track easterly waves all the way across Central America from the Atlantic into the eastern Pacific, where they reinvigorate. Another view that I'm going to talk more about here today, which I'm a little bit more favorable for, is that East Pacific easterly waves are generated and can be generated through purely local processes in isolation from what's occurring over Africa and parts of the eastern Atlantic. And I've done some work on this, basically starting from my PhD research at the University of Washington with Dennis Hartman back in 2001. But we've done a lot of work on this recently that has also helped to inspire others to do work on this topic. So I really like this idea here as far as local generation mechanisms. But ultimately, I think what the conclusion that I'm going to come to is possibly both of these are important at the end of my talk. Okay, so to think about the local generation of easterly wave idea, I started first thinking about this based on some work that was done over Africa, actually. So this is a map of Africa, and the black and grayish areas are topography. And of interest is this region right here. So this region that is labeled R2 is called the Darfur region of Africa in southern Sudan. And this region, and if you jump over to this plot, has a very, very strong diurnal cycle of precipitation. So there's very, very strong diurnal precipitation generated over the mountains every day. And then this precipitation propagates towards the west. And as it propagates towards the west, it can actually be a seeding mechanism for African easterly wave generation. And one group that showed that very nicely was a group that worked with Chris Thorncroft at the University at Albany in New York in the United States. And what they did is they took a very, very simple atmospheric model, an atmospheric model that essentially has no moist convection, no precipitation processes within it, a dry model, relatively coarse. It has a grid spacing of like 200 kilometers on a side, something of that order. And they took this model and they did a very simple experiment. So they forced this model with a patch here of strong convective heating, latent heating in the atmosphere, right over the Darfur region. And when they forced the model with heating right here that represents the diurnal pulsing of convection, they got the development downstream of easterly waves in the model. So this provided some evidence that a very strong diurnal convective source can potentially force easterly waves downstream in the model. Over Africa, there's an easterly jet here called the African easterly jet that moves downstream of this Darfur region. So we thought that, this is interesting, maybe something similar, maybe happening here in the Eastern Pacific to seed East Pacific easterly waves. So the region that we were particularly interested in is the Bight of Panama region. So this plot here shows a climatology of precipitation in the Bight of Panama region. Very high precipitation over the topography of Colombia and also downstream into the Eastern Pacific. And what's even more interesting about this region is that if you look at the diurnal cycle, this is longitude on this axis, so this is 70 west to 95 west. This is local time on this axis. This is 10 a.m. local time, going to midnight and then, coming back around again to the next day. And what you can see here is that there is a very strong diurnal cycle in this region, and this precipitation, slants upward to the northwest. And what this is indicative of is westward propagation off the coast that moves at about 15 meters per second. So there's a very strong diurnal source of precipitation here that is causing convective disturbances to propagate into the Eastern Pacific over the Bight of Panama. So we were thinking that maybe this could be a important generator for easterly waves, much like we see over Africa with the diurnal cycle there. Just some a brief proof of concept that this might actually work. There was a paper. Actually, I don't think this is submitted yet, but this is some work by Victor Torres and Chris Thorncroft in 2018. Essentially the same model that was used over Africa, but now they're looking at the Eastern Pacific. And in this particular paper, they put a strong convective heating source over the Bight of Panama. And in this dry model without any precipitation, just like over Africa, what you can see is the generation of these tilted disturbances over the Eastern Pacific that look like easterly waves. So this is at least some tantalizing evidence that maybe the Bight of Panama might be a seeding region for generation of easterly waves over the East Pacific. I'll talk a lot more about this process in detail in the next several slides. Okay, so now I'm going to talk about what I've done with some of my students to assess this process. So this is, first of all, some work that I've done with Adam Ridbeck, a former student of mine who's now at the Naval Research Lab in Alabama in the United States. And what this plot shows is a particular point in time, from June 25th through like July 20th of one particular year. I can't remember what year this is, but this is a year that there was a genesis of Tropical Cyclone Elida over the Eastern Pacific. This is longitude, and this vertical line here essentially indicates where the Bight of Panama is. And what you could see here is westward propagating disturbances that move from this region into the Eastern Tropical Pacific. Interestingly, you don't really see much. And this here, I think, is a rotation plot, a vorticity plot showing the rotation of the disturbances. You don't really see much evidence. Maybe one event here, possibly this event of rotational disturbances propagating from the Atlantic into this region. It does seem like much of the activity here that's propagating westward associated with easterly waves is initiated right here in the Bight of Panama region. So this is not conclusive, but some evidence that this region could be seeding westward propagating disturbances. Yeah.
Are the vorticity graphs filtered?
This one is not filtered, but the other graph that I showed, that was filtered, the 3 to 10 days, yeah. But this one is not. Okay, so motivating questions. based on this. One is, how do Bight of Panama convective disturbances transform into easterly waves, if you know that's indeed the source? You know, so how does that happen? And I'll talk about that. The second question is, if we have a model and we somehow remove this really strong source of Bight of Panama diurnal convection, will easterly waves in the East Pacific be strongly diminished you know, by removing that you know, forcing source? And so that's another question that you know I'll get at here. Okay, so first of all, let's think about the first question. So how do Bight of Panama disturbances translate into easterly waves? So what I have plotted on here is the early life cycle of an easterly wave in observations, and not really observations. It's you know, some of this is reanalysis, which you could argue is not real observations, but anyways, you know, you could think about these as being observations. And what I have shown on here are 6 panels of an easterly wave evolution. The first panel here, you have a region of enhanced precipitation. It's kind of hard to see the contours, and enhanced rotation sitting here right in the Bight of Panama. So that's like, you know, the first point of the life cycle. And then as time marches on, you see that this disturbance gets further and further away from the coast. So for example, you know, right here, it's, you know, sort of in the region just to the south of the Papagayo Jet, you know, right at this location. So one thing you can see here obviously is that there does seem to be a coherent pathway of easterly waves that translate back to the Bight of Panama in this you know, composite life cycle of easterly waves. But the other really interesting thing here is that somehow, you know, as these waves leave the coast, they start out reasonably circular, and then once they get over here near the Papagayo Jet, they start to take on this tilted structure. So the first thing I'll talk about here is, you know, so why do they take on this tilted structure? And to do that, this is, you know, my only scary equation that I'm going to show in this talk. We actually looked at the vorticity budget. So vorticity is a you know, measure of rotation, and so we're thinking about, you know, what causes you know, rotation to be maintained and develop within disturbances. This is the tendency of vorticity, and then 2 terms that I'm going to highlight here that are extremely important for generating rotation with the easterly waves are these 2. This one is horizontal advection. So basically this represents you know, bringing vorticity horizontally from other regions across a strong vorticity gradient into the wave in order to generate vorticity. So that's one way. Another term that's important for generation of vorticity is something that I call stretching. And this term is actually within the waves directly attributable to convection. So where you have convection, you have latent heat release. That latent heat release within the waves tends to be balanced by upward motion. So this is an example of a vertical velocity profile within the waves where you have convection. And then this upward motion, if it has some variation with height, you see it's stronger here and weaker here, could cause the column to be stretched out. You know, so you see here that, you know, air is moving faster upward at the top of this wave than the bottom. You could stretch out the column, and that's actually one mechanism for generating rotation within the waves. And, you know, it's called a stretching term. So that's going to prove to be extremely important within these disturbances for generating, you know, both the strength of the waves and also the tilt of them. And then there's other terms here that I'm not going to talk about that aren't quite as important. Okay, so for generating, so you can see it on this slide here. I showed this plot before. This is a typical easterly wave structure. The easterly wave starts out down here more or less circular, but then it, you know, gets a tilt as it moves further off the coast. And the process that seems to be most important for generating sort of this tilted, you know, southwest-northeast structure of the waves is stretching. And the reason that this wave gets stretched is that you tend to get precipitation within the wave having this really, really interesting split structure with precipitation in the wave occurring near the coast and also in the southwestern part of the wave with a minimum in the middle. And so I'll talk a little bit about why precipitation has that sort of strange dipole like structure. But regardless, if you have this distribution of precipitation in a wave, it drives vertical motion where the precipitation occurs, and it actually causes generation of vorticity or rotation at my laser pointer is going out. Rotation at these two different parts of the wave that help to cause it to stretch out. This bottom left plot is a vertical cross section. So if you look along this magenta line here and look at a height versus I guess it's not longitude, but height versus space cross section, you get this stretching term having this particular form here. So you see that there's strong generation of rotation and vorticity on the lower left side of the wave and strong generation of vorticity on the upper right side of the wave. So because you have precipitation in this configuration, you tend to enhance vorticity and rotation that tends to spread the wave out from northwest to southeast. So why is convection favored in the northeast and southwest parts of the wave? I'm not going to go through this in detail. It's very complicated. It's both a combination of dry dynamics and also advection of moisture that tends to support convection in two different parts of the wave. So if you're interested in reading about why you have that split structure, please look at this paper in more detail with one of my graduate students. Okay, thank you. Thank you. Okay, so that's how the wave becomes tilted and the role of vortex stretching in that. The other kind of really cool and more interesting thing maybe that I wanted to talk about here is how important really is the Panama Bight region for a source of easterly waves. And for that, we decided to turn to a model. So what we're going to show here are some experiments with a model called WRF, Weather Research Forecast Model, that was developed at NCAR in the United States. And we're going to run this regional model over this domain that you could see here. This is our control simulation with reasonable, realistic topography in Mexico and Central America. And we're also going to run this model in another configuration where we essentially flatten land over the Isthmus of Panama and northern South America. And the idea here is that if we flatten land, we can reduce the strength of this diurnal convective disturbance that's generated in this region that is seeding easterly waves. Now, there's other ways you could do this that we're also exploring currently, but as I'll show you in the next slide, this does a reasonably good job of reducing easterly wave activity in this region and the diurnal cycle in this region as well. Okay, so just to show you that this model does produce reasonable looking easterly waves, this is like the observational plot that I showed before, but it's for the model, and you get generation first of disturbances in the Bight of Panama that then move off towards the west, and then they gain a tilted structure as they get into the Papagayo Jet region here. So they look like disturbances that we actually see in observations. Okay, so first of all, has our removal of topography killed the diurnal cycle and this diurnal source of convection? So this is a plot that tries to make that case. As with most models, the model is not perfect. It doesn't do a perfect job of simulating things like the diurnal cycle in this region, but it does have a diurnal cycle of convection in this region. Upper left here is observations of precipitation showing a composite diurnal cycle with generation over the Bight of Panama and westward propagation of the diurnal cycle. So that looks, like we saw before. This is what the control version of the models look like with full topography. You could see some differences. The timing is a bit off. Convection initiates in the Bight in the model later than it does in observation, so that's one difference. You could also see that it's a bit weaker in terms of the diurnal cycle in the model than observed. So there are some differences, but this model does have some semblance of a diurnal cycle in the Bight of Panama. When you remove topography, the diurnal cycle pretty much completely goes away in the Bight of Panama. So we do seem to have removed this diurnal source of convection by flattening topography in the model in this region. Okay, so this is probably the most important slide that I'm going to show you as far as a result. So this shows vorticity, some measure rotation in observations here. And again, this is time, and this is longitude. So you can see here these discrete periods of westward propagating disturbances in a vorticity field, which are easterly waves. This plot, again, is not filtered. I think this is the total vorticity. This is the control experiment that has full topography over Mexico and Central America. And so you could see that it produces pretty reasonable easterly wave activity that moves westward. And this is the model where we have removed this diurnal source of convection by flattening topography. And what you can see here is that easterly wave activity has been substantially reduced. So this points to the fact that, suggests at least, that Bight of Panama diurnal pulsing is an important seed mechanism for easterly wave activity in this region. Now, if you look closely at this plot, you can see that there are some disturbances moving in from the Atlantic, further east over the Atlantic into the domain that then strengthen the eastern Pacific. So we haven't completely gotten rid of all easterly waves in this model by our experiment. And so this suggests that possibly both of those hypotheses that I pointed out before could have some merit, that the Bight of Panama can be a local generator of easterly waves, but you can have disturbances propagating from further out that come into this region that do seed easterly wave formation. So it could be both, and that's what this experiment actually suggests. All right, some caveats here about our experiment design. So our results with the model are suggestive, but they're not conclusive. So one problem is that removing topography in the model not only removes this diurnal source of convection, but it also changes the winds, background winds in the model quite a bit. So you could argue that we haven't cleanly separated yet the effect of diurnal pulsing of convection from background wind changes by removing topography when isolating the effect of easterly waves. And so that's one thing we want to address.
Did you remove the topography all at once, or did you slowly remove it?
We moved it all at once. So it's...
I try slowly removing it.
Yeah. So more of a gradation.
The background winds will come to equilibrium.
So we want to address that. Maybe possibly using an experiment like that. The other thing that we have not isolated in this experiment is that I was arguing that the Bight of Panama was the most important source of convective pulsing, but there is also generation of convection along the north coast of South America. There's generation of convection in Costa Rica, on diurnal timescales. So our experiment really hasn't isolated Bight of Panama itself for a seed mechanism for easterly waves. There are other regions that can contribute to convective initiation as well. And then also there's questions about sensitivity to model physics. So our model is imperfect. If you ran it with a different convection parameterization, maybe you get a different answer. So there's issues about that as well. And then the other thing that is really, really interesting to me in this region is that there seems to be interactions between the easterly waves and the Papagayo Jet, the jet that often flows through the gap in topography between Nicaragua and Costa Rica, that we really haven't wrapped our head completely around yet. So for example, with my student, Justin Whitaker, we actually looked at a case study of an easterly wave that propagated into the region of the Gulf of Papagayo and actually excited a strong Papagayo wind jet event. And we suspect that the excitation of the Papagayo jet is feeding back positively onto the easterly wave. But we really don't have, as of yet, a really good understanding about how that interaction actually occurs. And one of the problems is that I noted this stretching term before, where you have convection helping to spin up rotation within the easterly wave, and one of the problems is that if we look at this stretching term and so the vertical motion that causes it in both observations and a high resolution version of the WRF model that actually resolves convection, we can see that in the Papagayo Jet region the vertical velocity looks very, very different depending on what model or observation that you actually look at. So we really don't know, given this uncertainty about vertical velocity profiles and convective heating, how the jet actually interacts with the easterly wave. And so this is something, that sort of leads into my next part that field measurements might help to address. Okay, so that leads me to this. So the final thing I'll talk about here is a field program that is currently occurring in the Eastern Tropical Pacific and also the Atlantic side, for that matter, called Organization of Tropical East Pacific Convection, or OTREC. And this is a 2-month experiment in August and September of this year. I'm going to go out to the field September 6th to Costa Rica to participate in this field program. There are participating scientists from Colombia, Costa Rica, Mexico, and the United States that are going to be out in the field, including several people in this room who are going to be participating in this. And the overall goal, is to study convective processes, including things like easterly waves, in the Southwest Caribbean and East Pacific. The lead PIs on this are Jelka Fuchs and Dave Raymond. Dave Raymond was on sabbatical here in 2014, or something. Oh, it was even longer ago, 2001, 2002, I think. Okay. So they're the leads on this project. Okay, so the overall science questions are, one, what are the factors that control the formation of deep convection in the tropical East Pacific and Southwest Caribbean, given that these are two very different regimes. East Pacific tends to be, more convective. Caribbean side is, more dominated by the Caribbean low-level jet. What form does convection take in these two regions? In particular, how do the vertical mass flux profiles, energy budgets, vary as a function of environmental conditions? I noted uncertainty in the vertical velocity profile, for example, and how easterly waves interact with the Papagayo Jet. So this is, one thing that we're going to look at in OTREC. And then, more generally, how do the interactions of convection with tropical disturbances work in this region, especially the tropical easterly waves, which is, the topic of my talk. These are actually some early pictures from the G5 aircraft, taken think this is August 7th, over a mission over the East Pacific. This is Jose is one of the main photographers for many of the pictures that we've taken so far. Okay, so what instruments are we going to have? So the main, one of the main platforms is the Gulfstream G5 aircraft that is operated by the National Center for Atmospheric Research in Boulder, Colorado in the United States, and that's a picture of the G5 here. What we're going to do with that is, primary measurements are dropsondes, and I'll show you the array that we're going to operate in. But we're going to use dropsondes to assess the moisture, vorticity, and energy budgets of these disturbances. We have special sounding sites in Costa Rica and Colombia that are going to contribute to this program. I'm going to spend some time in Santa Cruz in Costa Rica during my time there. We have GPS, augmented GPS column water vapor measurements, and also surface met stations associated with the program. And then we also have oxygen isotopic measurements that are being augmented in both Costa Rica and Colombia as part of this, and ANA is contributing to that. Whoops. So we have three defined focus regions to OTREC that might help to answer some of the questions that I provided before. One of the regions that we're going to focus on is the Bight of Panama region right here in a box we call B1A. And we have set patterns within these boxes where we're going to drop sondes over the course of a mission. So what this is going to allow us to do is have a net array of sondes drop from 40,000 feet or so up in the atmosphere. That's going to allow us to derive budgets of vorticity and moisture and things like that. This is another box here in the Caribbean that we're going to focus on. And then we also have another box right here that's a bit larger. You can see the array here. And this is going to help us focus, for example, on interactions between easterly waves and the Papagayo Jet, as the waves, sort of propagate off towards the northwest into the eastern Pacific. So we have some really interesting early cases already of convection in this region. This, for example, shows an early flight, August 7th, one of the first flights of the experiment. And in this case, the airplane is right here in this particular scene. We're flying this box off the west coast of Central America. There are actually wind vectors on here that give an indication of some of the data that was collected by the aircraft when before it got to this point. And so at this time there was also a really interesting mesoscale convective disturbance that had propagated into this region from the east that we're sampling. So this is going to provide a really, really nice data set to do things like derive the vertical velocity structure across this disturbance that will tell us, for example, how it might be interacting with, the large-scale flow and gap winds and things like that. And this shows an example of an early radar cross-section from the flight. At this stage, the aircraft is up here, something around 40,000 feet high or so. And this is the W-band radar from the aircraft. Sea surface is down here. And we sampled this disturbance, right here. And what you could see is that there's a very, very strong, what we call stratiform looking structure with a large anvil up in the upper troposphere, middle troposphere. There's a lot of attenuation, but you can see some evidence of a melting level. And then it is raining down here, but the radar probably can't see very well down here to sea surface. But a very top-heavy looking cloud structure and presumably vertical velocity structure. Okay, so let me conclude here. So easterly waves, so one of the big messages from my talk is that easterly waves in the East Pacific appear to be seeded in many cases by convective disturbances originating in the Panama Bight. And so we've shown this, both in observational analysis, looking at budgets of rotation, but also in models. And in particular, our modeling experiments that reduced or removed this very strong, source of convective forcing in the Bight of Panama indicated a substantial reduction in easterly wave activity. Modeling experiment, as I mentioned, had some caveats involved that we want to work on, but it's somewhat suggestive that this region and convective forcing near the coast there is really important. And then the other thing that I showed you is that as these waves move away from the coast, the amplitude of the waves increases due to convection, and also they gain this northeast-southwest tilt due to vortex stretching, occurring to precipitation, being just distributed in sort of this dipole-like pattern across the disturbance. But there are a lot of loose ends, and I've alluded to some of these when I was talking. One thing that I really, really want to get my head wrapped around is the importance of the Papagayo Jet for easterly wave intensification. One of the first things that I brought up in this talk was that the mean flow is an important mechanism for easterly wave energy extraction. And the Papagayo Jet seems to be in a prime area for producing a very strong wind gradient on which the easterly waves can grow. But I don't think we've completely characterized the actions of this jet yet. So the Papagayo Jet can exist before the wave gets there, and then if the wave gets there, it can actually strengthen the Papagayo Jet. So there's a lot of really interesting interactions here that we want to characterize in terms of wave generation. I mentioned imperfect model design. The model results that I showed, one, changed the basic state in addition to reducing, convection on the coast of the Americas. So that's something I want to address. But also we want to run more simulations with no convection parameterization at all, where you explicitly resolve convection so that you can actually remove much of the parameterization problem from the simulation of easterly waves. And so that's another thing that we want to look at. I mentioned vertical profile of convective heating in developing easterly waves is a big question, depending on what model and what observational product that you get. You get a very different vertical profile, and this has large consequences for the vorticity budget of these disturbances. So that's a big thing that OTREC might be able to answer. And it's actually a big question in general about the Eastern Pacific Intertropical Convergence Zone. There was at least a big debate in the scientific literature about 10 years ago about what does the vertical profile of convective heating and vertical motion look like in the Eastern Pacific Intertropical Convergence Zone. There were two camps. One camp thought heating was, and vertical velocity were very bottom heavy. Another camp thought it was very top heavy. So this is still, a bit of a debate and something that OTREC is going to, help us to answer. And then looking, forward into the future, into the next 20, 30 years and beyond, one thing I'm becoming interested in is what is going to be the fate of easterly waves in this basin in the presence of anthropogenic climate change. There's some evidence that easterly waves are, going to be, shifted southward off of the coast and more into the, ITCZ and, near equatorial region of the Pacific with climate change. So that's, one thing to look at. Another really interesting thing to look at for me personally is that we've done some work recently on other tropical disturbances that suggest that the strength of wind associated with the tropical disturbances might decrease in intensity, even though precipitation variations with the tropical disturbances might go up. So sort of the ratio of precipitation to wind might change in a future climate. And I'm curious whether or not this is actually true in the Eastern Pacific as well in a future climate. And if that were the case, that the wind variations went down associated with easterly waves, that could have a lot of important consequences for things like the genesis of tropical cyclones in this region. Given that coupling to the sea surface and wind-induced coupling to the sea surface is an important factor for intensification potentially. So that's something that we really want to look at. And in general, I mentioned OTREC. OTREC may be able to shed some light on several of these issues here. Probably not climate change since it's a 2-month period, but at least these first three. So with that, I think I will say thank you, and I'll show a nice picture of Lake Tahoe here that I took in December, and I'll take any questions. Thank you.
¿Alguien tiene alguna pregunta?
Thank you. I'm a meteorologist, but I'm as far away from you as humanly possible. I study the flows around cities. And so I found this very well organized, and I learned a lot. And two things popped out of me, but they're sent out of ignorance, not for any ulterior research agenda. Why the Bight of Panama? It's such a minute landmass compared to the shape of South America. And when I compare that to the shape of Africa, it seems to me they have a very similar shape. Could it be the origin of these are the coast of South America and not really the Bight of Panama, not really that puny landmass?
That's a good question. I mean, I don't think we completely know why precipitation is so localized right there. But, Brian Mapes and collaborators have looked at, what generates those disturbances, and they start as heating over the mountains, over the Andes of South America. So, during the day, there's elevated heating right over the mountains, and those the topography there, given the height and the shape, actually forces an atmospheric gravity wave that propagates off the coast at 15 meters per second. So there's something special about the shape of the land mass and height of topography there that's ideal for generating this gravity wave.
And secondly, why do they not move just from east to west? Why do they follow the coast of Central America? Could it be that there's additional heating that's sort of causing them to hug the coast?
I think you're right. So one thing that we were noticing in our model experiments, and I don't think it came out in any of the slides here, is that when these disturbances reach the coast of Panama and Costa Rica, it seems like they're reinforced by diurnal convection that's occurring in those two places as well. So that's one of the things that's a little ambiguous about this is it's not only the Bight of Panama, but maybe our experiments haven't isolated that effect from other regions. Yeah, I think you're right.
Also, I want to say I never understood vorticity stretching, but your diagram did it, and I have a follow-up question later on.
Okay.
¿Más preguntas?
Thanks very much. Excellent talk, very clear. And I have several things that we can talk later at lunch, but perhaps you can, you mentioned that OTREC was about looking at the two very different regimes across Central America. Maybe you can explain a little bit for people that don't know much about the convective regimes there. That's one thing. And then the other question that I have is to try to relate this to the actual cyclogenesis. And how can we say, sort of predict when these easterly waves that are forming there would really enhance circulations in a way that they will become seeds for tropical cyclones, because we would have, in principle, if it's just diurnal cycle, a lot of waves, but not that many, no?
Yeah.
Tropical cyclones.
So presumably you need, for cyclogenesis issue, you need relatively strong waves, and there's different ideas, I guess, on how the easterly waves foster cyclogenesis. And there's these hypotheses by Mike Montgomery and Dunkerton, where the easterly waves, strong easterly wave forms so sort of this protective pouch around the developing tropical cyclone and insulates it from dry air in the environment and things like that. So presumably, you would need, a really strong diurnal disturbance. So certainly not all diurnal disturbances here form into a tropical cyclone. I think it's the stronger ones that the days where the diurnal cycle is stronger that have the capability to actually seed easterly waves, whereas the other days where diurnal convection is weaker, I think those disturbances probably die out. But as far as the east versus west, something that's always fascinated me, I guess, about the Caribbean is that sea surface temperatures there are reasonably warm, but there tends to be a relative lack of deep convection there, and also northward into the Gulf of Mexico, versus what we see on the eastern Pacific side. And so, earlier climate models at least had an issue with this, in that they would tend to produce too much precipitation over the Caribbean, but they were biased high, where there shouldn't be that much precip. So I think a basic question for me is why, given and not that dissimilar sea surface temperature state, do you have suppression of convection on one side, relative suppression of convection on one side, and relative enhancement on the other? I think that's sort of the issue to me. And maybe you have some ideas.
Okay, since I have the microphone,
yeah.
I want a follow-up question with respect to the tropical cyclone intensification that I thought was interesting. What you said, that perhaps the interaction with the Papagayo Jet might provide the additional push to get that going.
Okay, so you think that might be something to pursue, yeah.
Yeah, so if we could also have a better handle on that variability,
right,
then there would be an interaction that might lead to a stronger circulation.
So just in the last day or two, I haven't followed it because I was traveling here, but there was a cyclogenesis event in the East Pacific. Further off. Okay, so it wasn't in the Papagayo region. So it was.
No, it was further west.
Because I was wondering if that, OTREC being out there could shed some light on that, but since it was further west, then maybe it's, yeah.
110, 115, 110.
Right, but anyways, the interaction with the Papagayo Jet sounds like a really interesting avenue to pursue, yeah.
Thanks for the talk and for bringing back the importance of the Papagayo Jet, because so far the jet is considered to be off in the season. So the jet is mainly active during the winter months, let's say from December to February. But what we've been observing in the data, in observation from the Met stations, is that the Papagayo Jet comes back again only for those days when the waves are active.
I see. And do you see the jet preceding the waves, or does the wave spark the jet? Have you?
Well, what we normally see, and we can discuss the data later, is that we have an activation of the jet once the convection has started.
I see. Okay. All right, that's interesting.
¿Alguien más?
Okay. There is an additional question here that says, is it more favorable for easterly wave to enhance the formation of a tropical cyclone in the Pacific than in the Atlantic? If it's true, why?
I don't know the exact numbers, but
I have the numbers.
You have, okay, but I think it's comparable, but maybe you.
Yeah, 70% de las ondas yo encontré del este en el Océano Pacífico llegan a ser ciclones tropicales. Y del lado del Atlántico, el 50% de los ciclones tropicales provienen de ondas del este. Más o menos es para que se den una idea. Las interacciones que ocurren en el Atlántico tienen que ver también con las latitudes medias, entonces por eso es que es menor el porcentaje. Y en el Pacífico, pues básicamente es la ITCZ and the easterly waves.
Hi, and thank you for your excellent presentation and sharing your knowledge with us. Well, I have two questions. The first, well, in Mexico, well, only for making some separation about the things that I'm clear. In Mexico, we have observed some easterly waves that reach the Yucatan Peninsula. So maybe we can say that this kind of easterly waves are purely from the, I don't know, from in Africa and the current Atlantic Ocean, or maybe we can explain some of this reason with this idea of the formation. This is the first one.
That's an interesting question. I would think, my initial reaction is that those waves are most likely coming from Africa. You know, maybe they get enhanced somehow through interactions with the flow in the Caribbean. But I'm trying to think if there's some other generation mechanism that's local to the Caribbean that could cause, I mean, maybe diurnal convection over the islands of Puerto Rico. Or I don't know. You know, it's my reaction is probably African easterly waves, but I can't rule out other things.
Okay. And the second one. Well, in the model we can see this strange of the vorticity, and we can infer that we have the rain before the wave. But well, I don't know. I want to know your expectation or your ideas about the Frank model in the 70s years that explained that it was this UV inverted pattern that have maybe some convection in front of the wave and behind the wave. Because I have watched some easterly waves that have this convection maybe in the line of the wave, maybe a little in front, a little behind. I don't know what's your idea.
Yeah, so it seems like, for example, if you look at Africa, over Africa, the phase relationship to the convection and the wave changes depending on whether you're in Eastern Africa versus Western Africa versus the Atlantic, and so there's a change in that phase relationship, and I think a lot of it has to do with the dry dynamical forcing being strong over Africa and weaker for generating vertical velocity over the Atlantic. For Eastern Pacific waves, I mean, it seems like it's largely, the precipitation being in phase with vorticity, although there's subtleties. Like I said, there tends to be a split. For example, and one of the things I didn't talk about is why there's an enhancement of precipitation in the northeast part of the wave, and we think that is partially due to dry dynamics, in that you get, you could use the omega equation and think about differential vorticity advection with height associated with the Caribbean low-level jet actually forcing vertical velocity in the northeast part of the wave. It was kind of a complicated thing to talk about, so I didn't dwell on that. But I think there's some interesting subtleties there in the Eastern Pacific, even though generally it's positive vorticity and positive precipitation.
Okay, thank you.
Well, you've just, I think, answered one of my questions, and that was whether the jet caused vorticity stretching that could enhance the...
That's right, and I think that, one of the things we're interested in is whether, when the Papagayo Jet enhances, whether or not that can enhance the stretching. But it depends on what the vertical velocity profile looks like. If the vertical velocity profile is downward in the lower troposphere, it would actually destroy vorticity in the presence of a jet.
In the upper part of the jet, after the peak.
Yeah, so that's why the vertical velocity matters, yeah.
Reason I'm asking these questions, and I'm studying splitting thunderstorms over cities, and I was wondering, and the editor of Monthly Weather Review keeps telling me things that involve vorticity stretching and vorticity tilting, and
Okay.
I'm not very good at that. And so I was going to discuss this with you afterwards, but what about the vorticity tilting term? That is a term in the equation, right?
Yeah, that was one of the things I ignored, so we looked at it, and at large scales, I mean, the scales we're looking at, it's not that important. But yeah, I think when you get down to maybe the city scale.
Is it possible our splitting thunderstorms are explained by some of the mechanisms you've seen here that create two areas of precipitation? Because that's what happened. The storm goes around our cities, Beijing, New York, and we get two precipitating cells on either side of the city. Again, we could discuss this offline.
Yeah, it could be, yeah.
¿Más preguntas? Okay, bueno.
Well, can I just say that, thank you very much for the invitation, and so I've always wanted to come to UNAM in Mexico City, and thank you very much for the hospitality. And the other thing I want to say is that I did take 4 years of Spanish in high school, and the first lesson, Spanish lesson that we had involved two people conversing in Chapultepec Park, and so ever since then I've wanted to come to Mexico City. So thank you.
Thank you so much. You're welcome always.